You may be wondering why am I opening every topic with a pun, but there was actually a research on that, a research on the effects of puns on educational quality. And they've selected like a representative number of students, around 100 I believe, and then a representative number of puns, something like 10. And then they tried to see how many of those puns have improved the learning process. And when they measured, well, no pun intended. And while that research is still ongoing, we go on to the patterns of software processing, which is the practice topic of the last level. There are many patterns in language processing, in compiler construction, software analytics, this kind of stuff. So I'm heavily cherry picking here and sort of jumping from one topic to the other, just to give you an impression that what kind of things exist there. But if you want to know more, obviously you can sort of Google up these terms and try to figure out these things on your own. The first topic is the grammar and the parser, right? So we have the grammar, we have the parser, and how they are related. So many of you used Antler, and that means that you are generating the parser from the grammar. But then, of course, there is this connection between the grammar and the parser that is harder to trace because it's hidden behind a tool which does pretty sophisticated job in order to enable certain things. But there is one easy way to make a worse parser than the Antler is producing, but still something that can help you to quickly get a parser out of some grammar that you're writing, so that you can then tweak the parser if you really want to, do some bespoke error handling or stuff like this. And this is called recursive descent. And if you've ever had anything resembling a compiler course, you've probably heard of recursive descent. And it works like this. If you have a production rule in your grammar that says A is a B, C, D, and C is a terminal, so it's literally that, and B, D, and A are non-terminals, then this literally is transformed into a function. Well, in this case, I'm doing a recognition function, right? So it's not a parser yet, but it's a recognizer or whether this is correct grammatical input. So in order to recognize if something is an A, you do the B, whatever B does, then you check that the next token is C, and then you check if the remainder is D, and well, that's it. Right? And this is a recognizer. If you want to do a parser, you need to do a little more dancing around with like local data structures and whatnot, but in general, this is exactly how it will go. If you do recursive descents, if you ever have any left recursion in your grammar, then this becomes immediately deadly for your parser, because, well, if you say that expression is an expression or plus expression, then in order to parse expression, you go into expression and you start parsing expression, right? What you get Stack Overflow, and not in a good way. And so Antler, for instance, detects these situations and does something specific to refactor your grammar behind the scenes in order to avoid that. And there is a generalization of this recursive descent thing, which is called parsing expression grammars, where you could have, so instead of a choice, they do the slash, which is a ordered choice. So they only try the second and third alternative, well, the second and third choice only if the first one is impossible, and they only do the third one if the second one is impossible. And then you can also do the exclamation mark is not, so you can check if the look ahead, if the next token or the next couple of tokens satisfy C. If they do, then the exclamation fails, right? And if they don't, then you go further. And then, of course, you can have the AND, which means that you parse with E and F either at the same time or at least from the same point. And sometimes it's useful to have two representations of the same piece of data. The next thing is whenever you're writing a parser, again, parsing techniques is a huge world. There are entire books like this big explaining to you all kinds of parsing techniques that exist in the world. But there are two very useful tricks that work pretty much with any parsing algorithm and are really good for to remember for whenever you are doing any kind of language processing. The first one is backtracking. And so whenever something fails, you don't fail the entire process. You fail that particular alternative, and then you go back and then you try it again. Usually you're trying something else, right? For instance, you can have a non-terminal that has several alternative definitions within one production rule, and then you try the first one. If that one doesn't work, you go back and then you redo it again. For instance, if you do a recursive descent with backtracking, the simple variant from the last slide that I presented had no backtracking implicitly, but you can build it in quite easily. Then if you have something that people are calling LLK grammars, which means that it's going top down, and that means that it's constructing things from left to right, and also has some limited look ahead. That means that you have guaranteed proven termination. Proven termination is very good because then you don't need to do anything, it just works. So it terminates. But it can be, of course, like very slow to terminate. But still, then you have guaranteed termination, which is a good thing. The second trick is memoization. There is no misspelling. It's really written without R. So it comes from a memo, so a reminder for you. So you are consuming the inputs and you are remembering all the things that you've done, and you know that at this position you tried to parse this non-terminal and it worked. And if it worked, here's a tree, and if it didn't work, then you remember that it didn't work. Right? So the next time you do, you go back. So in this case, for instance, there is an example with an if statement, which first has the variant with an else part, and second, then it has the thing without the else. So if else fails, let's say, then we go back to the point where it started to, it was about to consume the if. And then the first four symbols are exactly the same as in the previous part. So that means that we have been at exactly the same place doing exactly these things, which means we just get them from the cache and that's it, we're done with parsing. So, for instance, if you compile parse and expression grammars with memoization and with backtracking, then you get pretty much linear performance, which is quite good. The next pattern or set of patterns that we will consider is about an abstract syntax tree. So it's the abstract syntax tree. The name is there for historical reasons. The fact that it's abstract used to refer to the fact that it didn't have layout right there in a tree, or sometimes no terminals at all, depending on your definition. But what if we want to do some refactoring based on that abstract syntax tree, right? Then we do need to preserve comments there. We don't generate comments when we are refactoring, well, probably not. But we want to preserve the comments that are already there because they are valuable pieces of documentation, right? So then we do sneak it into the abstract syntax tree, and nowadays nobody bats an eye if you have a comment node in your abstract syntax tree. The syntax used to refer to the fact that the tree largely follows a grammar, mostly because if it doesn't, then you need to do something. Right? You've been through that, at least some of the groups, where you realize that the tree that the Antler is giving to you is not very comfortable for you to work on. So you've written a visitor or a listener to look into that tree and then to construct the tree that you want. And that tree, well, it doesn't really have to have any relation to actual syntax of the language. That's just your intermediate representation. So if you want more details, if you want different positioning of data and different separation of different concerns, it still is okay to call it an abstract syntax tree. But of course, the syntax part will have no real meaning. The tree part means that it's the tree as you have trees in mathematics. It starts somewhere, there is a root, and it goes from the root only one way. And there are no loops, and it doesn't go anywhere else. Well, that's also not always the case, because quite often we want cross-references. We want, for instance, to have like one place when we define some field in the data division, and there are many other places where you refer to it from the procedure division, and maybe you want that that relation there explicitly, right? And then it stops being a tree. But it's still called abstract syntax tree. And there are basically like two ways to build the abstract syntax tree. But before we go to that, I just want to say that AST design is a design problem, so it needs to be approached as such. There is some context of this problem, usually because there is some influence from the syntax perspective, from either the form of the parse tree or the grammar that you like or whatever you want. In order to design a good abstract syntax tree, you need to remember things from the data structures. Well, data structures and algorithms, that's usually how these courses are called, because they are linked, right? You simplify the data structures, maybe your algorithms will have to become harder. You want your algorithms simpler, maybe you need to complicate your data structures. This is a balance. So there will be some data structures and you need to remember what you learned there. And if you've had any course about design or with design elements, in particular object-oriented design, because most of the time you will be implementing it in an object-oriented language or language with some OO modeling tools and arsenal available, then that would be very helpful. Just remember that you are not just creating a dead data structure, you will need to do something with it. And by doing something with it, I mean mostly traversing it, right? So there is a tree. That's why it was a tree, right? You start at the root and then you go, and then at some point you know when you are done. So in many cases, ASTs still pretend to be trees, even if they have some loops, but they know how to organize these loops so that you don't get in trouble when you're traversing it. The usual strategies for traversing it are the top down and the bottom up. That's easy. You start with a root or you start with leaves and then you go up. But there is also a very useful one, innermost, when you start from the leaves and you maybe even changing the tree on the way up. And then once you're up enough, then that means that all the places that you have visited so far, they have been looked at and looked into. And then you can have breadth first. So innermost is a sort of a variation of a bottom up, and a breadth first is a sort of variation of the top down. When you first go through all the blocks that you have in your system in order to see if they define any, let's say, local variables. Right? And then by having that knowledge at hand, then you go deeper one level, and then you do something on the level of statements, and then you go to the level of expressions and so forth. So that would be a breadth first exploration. So I promised two ways to make an AST, and here they are. They are homogeneous and heterogeneous. The homogeneous AST means that you have one class that's called node. And that's it. All the nodes in your AST will have the type node. Then you have one field there that is called content. You can call it whatever you want, but I will call it content. And this will be like the thing, the data that is stored in that node. If the language permits, you can keep it untyped. If the language does not permit, you propagate it, you promote it to the top type that you have. So in Java, that would be system object. In the same node, you also have children, because some nodes will have children, and that's just a collection, again, a very generic collection, either a list of nodes or an innumerable of nodes, some way that says that you can iterate through it later, but everything there is a node. So that makes it easy, right, to couple it back. If you do this, then it becomes somewhat easier to program uniform operations, right? You literally have one class. So you implement it there, and then it just works everywhere. No casting, nothing, no type checks. You still need the structure to come from somewhere, and that structure needs to go into the content field, right? So quite often this is chosen where the content can be immediately inherited from the parse tree or from even the token stream, right? If your content can be a token, right? If that's it, then this is perfect, right? You define one more class, Your content has the type token, or whatever the type of the token is, and that's it. You have the children, and you specify everything in one place. It all works out. If you need a different complex structure, then whether that structure goes into the node or the content doesn't matter that much. So the heterogeneous one is that you can have this node thing, but then it will be more like an interface or maybe an abstract supertype, superclass, somewhere high up in the hierarchy. And then you have separate classes for each type of the nodes that you actually want to see. If you have a Boolean expression in your conceptual modeling map, or maybe even in your grammar, then you will have a class that's called Boolean expression. And it will probably be like a sibling class with a string expression and arithmetic expression. And together, they will all be subtypes of expression in general. Right? And then you will have some hierarchy of those things where, for instance, a while loop can be a subtype, subclass of a statement. And a statement is then a subclass of something else, and eventually they are all subclasses of node. On the downside, you have much more classes. On the upside, you have full flexibility. So you can specify the methods exactly where you want them. You can make it work differently for different nodes, and you can enforce some type checks on the level of the language that you're using to write your language processor in. Right, so you can ask Java, for instance, to say, no, this is a while loop, and my content in a while loop is an Boolean expression and a statement block. That's it. So you can't put statements in there, you can't put string expressions there, and if you try, Java will just stop you. The next pattern is a symbol table. So Baby COBOL has only one global scope, so you could have gotten away with just one symbol table that just lists all the variables that you can have with their types, and that's it. And then you would store it at your visitor or interpreter, or maybe even make it static so that you can easily access it from anywhere. In more complex languages, you will have different scopes, right? And these scopes can be even dynamic. So in Java, for instance, you have at least these three. So you have the method level scope for like local variables. You have a method, and inside that method, you define a variable. You exit the method, that's it. And it's inaccessible. You can have on a class level, you can have private attributes, also variables, but also, for instance, methods that you can only call while you are inside the method, inside the class. Right? And then you can have, on expression level, you can have lambda parameters. And then you can have things like, for instance, it's a lambda expression that takes an A and it prints A plus B. Right? So the B comes from the outer scope. So that should be fixed by the time you define this. And so the value of B at the time of the definition of this lambda function goes into the printing function. But the A, that's a parameter. So that only exists within that scope. If there was another A, then this will be overshadowed by it. And for the symbol table, so you've seen that it's useful even in such a simplistic scenario, but in the case where you have like nested scopes and a stack of scopes and whatnot, then it will be even more useful. And just watch out for polymorphism. So don't trust the name, right? The name separate different things can have the same name, and you still want to distinguish between those while you are processing the language. Then, well, I mentioned the types when we were talking about the symbol table. So what about the type system? A type system is something that needs to be designed also and thought through when you are making the language, or when you are implementing the language. Then it's only partially designed, but mostly just understood. It also can be formalized. So in some cases you will see like scarily looking, but still very straightforward ways to just write down the types that you can have for for the thing. Types usually form a lattice, sometimes drawn as a Hasse diagram, just because it's a partial order, right? Some types can be promoted to other types, and then on the top you have the top type, which is sort of like system.object in Java. And then in the bottom you have the bottom type, which is void, right? It's a type of which you can have no instance. And then you have some rules for computing the types, and these rules can be extremely simple, like if you have a true, that has a type boolean. But it's still important for your type checker to understand that this is the case. They can be slightly more complex with conditions attached to them. For instance, if you have not expression, that has a type boolean only if expression already has a type boolean or can be promoted to that type. And they can be even more complex in the sense that you need to think about that. Well, I said it needs designing. Right? So for instance, if you have one expression that has a type integer and another one that has a type string, then what's the type of one plus another one? Right? What's the type? What happens if you add a string to an integer? In some languages, like in Java, it's completely impossible. They will just not compile. They will say that this is wrong. In Python, they will try to run it, and then something will happen at the runtime. In JavaScript, it will happen fine, and then of course there is this famous discrepancy in JavaScript that if you try to add an integer to a string, both will be promoted to a string and then concatenated, because plus means concatenation for the strings. But if you do a minus, then both have to be promoted to a number. So there is no Hasse diagram, but there is more like anything. We can try to fit anything into anything, and only if you fail the conversion itself, then something happens, and then even then, something happens means that you just go to the bottom type, which is none. The last set of patterns is about interpreters, or in a very broad sense, virtual machines. First of all, the most simple way to build a virtual machine on an interpreter for your language is to do syntax-oriented evaluation. So you have some syntax, and you know that, okay, first we do this, and then we immediately execute that. That sort of works for some languages more comfortably than for others. If you have something like a protocol, or I don't know, some simple script that has like a number of commands that need to be executed on some data, something like a job control language scripts, or batch scripts, or text editing commands, right? You take the first command and then you execute it, and then you take the second one and then you execute it. That's completely fine. You don't need any like global scope or anything to continue doing that. There is also the next level there where you do the tree-based translation, when you are first making a tree and maybe annotating it with all kinds of stuff, and then you do the interpretation, and maybe either before the interpretation or maybe during, or maybe instead of the interpretation as such, you do rewriting on that tree. So you're literally simplifying the tree further and further until it collapses to a one node with a result of the computation. And finally, you can have bytecode level interpretation, which basically means that in your compiler itself, you just express then the AST that you have, or some intermediate representation that you have, in a form of bytecode commands. And then when you want to actually execute them, then you interpret them. Right, so then you're basically building a compiler, a translator from that tree or from that language, whatever you had back then, into some fake imaginary bytecode of something that you will be executing as well. And then there is a big, holy war, of course, going on with the virtual machines. Some of them are stack-based. So JVM, for instance, is a stack-based machine. So you always have a stack, and something is happening there. If you go somewhere, then you put the return value on a stack. If you return from somewhere, you take that value there from there in order to know where to return, and then you put the return value on the stack. and so forth. And there are some register-based virtual machines where you don't necessarily have a stack. You may have some data structures floating around, but you mostly deal with registers, and you have the let's say a limited number of local variables, right? So think of them as local variables, and then you will not be that far off. So LLVM, for instance, that's a register-based virtual machine. But Erlang and Lua and some other languages, they also go for register-based machines, because the abstraction for the register-based machines is harder to get right. But if done right, they are usually more optimized. So then it's easier to optimize. So the well done register-based virtual machines are usually faster than the stack-based ones. Just for you to know. To conclude, there are many patterns in compiler construction in the narrow sense, and in language processing in a broad sense. We've seen some of those, so we've seen some on parsing, and if you remember, if you think back to the parsing in the broad sense, then there is a bunch of patterns on itself. So parsing in the broad sense is sort of a mega pattern, which tells you how many of the existing patterns fall into place there. Then we've seen a couple of patterns on the structure of the abstract syntax tree, or some form of intermediate representation, and a bit talked about symbol table as well. And then we talked a bit about the virtual machines, or the code generation, or the interpretation part. If you have any questions, you know where to find me.